Let's find a general expression for the energy eigenvalues of the quantum harmonic oscillator. Over here I've written the time-independent Schrödinger equation in blue. We're going to be using this in a derivation in this video. I've also written an analogous eigenvalue equation for the number operator. So the time-independent Schrödinger equation is actually an eigenvalue equation for the Hamiltonian operator. We have the Hamiltonian acting on one of its eigenstates, and that is equivalent to an energy eigenvalue multiplying the eigenstate. And over here we have the number operator acting on the same eigenstate, and that is equivalent to this eigenvalue of the number operator multiplying the eigenstate. So the eigenstates are actually the same. The Hamiltonian operator and the number operator share the same eigenstates, but the eigenvalues are different. So we have different eigenvalues over here. But this eigenvalue is associated with the energy, but this is associated with the number of the state. And in a previous video, we found some restrictions that we can put on n. N, we know, has to be a real number. And the reason it's a real number is because this is a Hermitian operator. In fact, both of these guys are Hermitian operators. And a property of Hermitian operators is that they have real eigenvalues. That is why Hermitian operators correspond to observables, things that you can actually measure. And real numbers are the things that we measure in experiments, right? We don't measure imaginary numbers in experiments. We measure real numbers. So the energy is something that you can measure in an experiment. And in fact, these are the allowed energy levels that you would get if you performed an experiment on the quantum harmonic oscillator system. So let's have a look at what we can do with these two expressions. We can actually take this definition over here and do some analysis. So the Hamiltonian can be expressed in terms of the number operator. So all you have to do is add a constant and scale this by a numerical coefficient. We just have h bar omega. That is just a numerical coefficient over here. And here we're adding 1/2. And if we actually expanded this out, we'd be adding h bar omega on 2. And it turns out that is the ground state energy of the quantum harmonic oscillator. And we'll get to that later in this video. So a thing that you can see over here is that if you were to commute the number operator with the Hamiltonian, you would actually get 0. So the commutator of these guys would be 0. These guys are commuting operators. And the reason for that is because all you have here are constants. You're just adding a constant. And constants can commute with operators. That is a very useful property because these are all real numbers. And real numbers, they satisfy the property of commutativity. In general, in quantum mechanics, you can't swap the order of operators. Operators are not commutative in general. But luckily for us, the Hamiltonian operator and the number operator, they do commute. And that is why they share the same eigenstates. You can think of these as eigenvectors. And I'm using Dirac notation over here. These are all represented by kets. So we have a ket, a ket, and a ket, and a ket. And the kets have labels inside them, and these labels are actually the eigenvalues of the number operator. So that's the labeling system that I'm using. So let's get to a very interesting derivation. Let's consider this time-independent Schrödinger equation, and let's substitute this definition of the Hamiltonian operator written in terms of the number operator. So I'll do that over here in red. So we're going to have h bar omega, that's the numerical coefficient. Then we're going to have the number operator. Then we're going to add to that 1/2. And all of this is going to be acting on an eigenstate. So this is an eigenstate over here. I'm using this ket notation, which is very useful Dirac notation. So that is the left-hand side of the time-independent Schrödinger equation. Now let's add the right-hand side. We have the right-hand side of the time-independent Schrödinger equation, which is just the eigenvalue multiplying the eigenstate. So what can we do with this? Well, we have a numerical coefficient. We can just divide both sides by that numerical coefficient. So that's going to give me E sub n divided by h bar omega on this side. But I also want to split this into two terms. I want to act with the number operator on the eigenstate, and I also want to act with this numerical coefficient of 1/2. So I'm going to split all of this up, and that's going to give me the number operator acting on the eigenstate plus 1/2 times the eigenstate. And that is all going to be equal to the energy eigenvalue divided by h bar omega, and that is multiplying the same eigenstate, labeled by lowercase n. So can you see what I've done here? I've just moved this h bar omega to the other side. I've divided both sides by that factor. So that's given me this. And then I've split this term into two separate terms. I've distributed this ket inside. So now the number operator is acting on the ket, and this factor of 1/2 is multiplying the ket. And what I can also do is I can move this term to the other side. I can subtract it from both sides of the equation. And then I can group those two terms on the other side of the equation. And that's going to give me this. I'm going to have the number operator acting on the eigenstate on the left-hand side. And that's going to be equal to, I'll put some brackets over here. So we're going to have this factor over here. That's E sub n over h bar omega. And then we want to move this term to the other side and factor out the half. That's going to be minus 1/2. And all of this is going to be acting on this ket. So can you see what I've done here? I've just moved this term to the other side by subtracting 1/2 times this ket from both sides of the equation. And then I've factored out this ket. I've grouped these terms together, and that's given me this relationship over here. But have a look at this. I have the number operator acting on an eigenstate. That's giving me some value, some numerical coefficient, multiplying the same eigenstate. That is the same equation I have over here. So what I have is this. I have n times the ket n. So I have an eigenvalue which is equivalent to all of this. So now what I have is, I'll write this in, let's pick a different color to distinguish this. We have n, this eigenvalue of the number operator, is equivalent to all of this. We have E n over h bar omega minus 1/2. And if I manipulate that slightly, that's going to give me n plus 1/2. So I just want to move this half to the other side. That's equal to En over h bar omega. And then finally, if I multiply both sides by h bar omega, that's going to give me this equation. The nth energy eigenvalue is equal to h bar omega times n plus 1/2. And an alternative way I can write this is using this convention. I can write this as 2n plus 1, all multiplying h bar omega over 2. So let's unpack what I've just written. What we've done is we've identified that this coefficient is the same as this lowercase n. This, all of these combinations over here, these combinations of numerical coefficients, they are the same as the eigenvalue of the number operator. So I've set lowercase n equal to this combination. Then I've just moved this half to the other side. That's given me n plus 1/2 is equal to this. And notice over here that the units cancel out. H bar omega has units of energy, and this is an energy eigenvalue that also has units of energy. So we have energy divided by energy, the units cancel, and over here we're left with a dimensionless quantity, right? Because this is just n. This is a number that is 0, 1, 2, 3, and so on. It is a non-negative integer. And how do we know it's a non-negative integer? Well, in a previous video, I actually did some algebraic working that showed that this has a minimum value of 0, and the only way that we can avoid logical contradictions is to ensure that 0, 1, 2, 3, and all of these natural numbers and 0 are included as possible values. So that's why n is always defined to be the all of the non-negative integers. That's a very important point to stress on. So luckily for us, the units cancel out. Now, why do the units cancel out? Well, the units of h bar are energy times time, and over here we have the angular frequency, so that's going to give us per time. So energy times time, per time, the times are going to cancel, and that's going to give us energy. So h bar omega has units of energy. You could write h bar omega in a slightly different form if you move some 2 pi's around. You could write this as h times nu, because h bar omega is actually defined as Planck's constant divided by 2 pi. And omega also has a sneaky factor of 2 pi inside it. It's 2 pi times the frequency. So that's just some points to consider when you're looking at this expression. So then when I multiplied both sides by h bar omega, that gave me this form over here. And I've written that in a slightly alternative way. I've multiplied the inside over here by 2, and I've divided this term on the outside by 2. So in fact, I've factored out 1/2. I factored out 1/2 from this equation. And what is this over here? This is actually all of the odd numbers. So you can write all of the odd numbers using this combination. If n is allowed to go from 0, so I'll specify this down here. N is equal to 0, 1, 2, 3, and so on. And you could also write it as n is an element of the integers which are non-negative, all right, a minus sign. Or actually, I'll just write a minus sign over here. So non-negative, the non-negative integers. That's some fancy notation for saying these are the integers not including the negative integers. So 0 and the positive integers. Alternatively, you could write that as n is an element of the set that includes 0 and all of the positive integers. That's an alternative notation. This is sometimes used as well, so non-negative. I'm just writing a minus sign for short, so we don't write negative up here. But it's 0 or all of the positive integers. So these are all various different notations for this combination over here. So n is 0, 1, 2, 3, and so on. So if we set n to be 0, 1, 2, 3, and so on, that's going to give us all of the odd numbers. So if n is equal to 0, we're going to get 1. And then when n is equal to 1, we're going to get 3. Then we're going to get 5, 7, and so on. So let's have a look at all of the possible energies. I'm going to start from the bottom and start from the ground state energy. So the ground state energy of the quantum harmonic oscillator is actually the case where n is equal to 0. Now, can you see what happens to this expression if n is equal to 0? If we set n equal to 0, then all of this is actually going to disappear. This 2n part is going to disappear. So we're just going to be left with 1 times h bar omega over 2. So that's h bar omega over 2. So if I write the subscript over here, I'll write E sub 0. That is equal to h bar omega over 2. That's the ground state energy. That's the lowest possible energy you can have if you are a particle in a quantum harmonic oscillator. Now, let's have a look at the first excited state. The first excited state is going to be 3 h bar omega on 2. So this is the next odd number. We've got an odd number over here. So this is n equals to 1. Now let's have a look at the second excited state. So the second excited state is going to be 5 h bar omega on 2. That's the next odd number. Now I'm going to skip ahead and let's have a look at what happens when we have the n minus 1th state. So you have n minus 1. What is that going to be equal to? And also, what is the nth state going to be equal to? And finally, what is the nth plus 1th state going to be equal to? So you have n plus 1 over here. So first I'll do this one in the middle. That is the same as the formula we have over here. So that's just equal to h bar omega times little n plus 1/2. So if we pick any arbitrary state n, this is just n plus 1/2. What about this one? This is 1 below. So if we put n minus 1 in here, I'll substitute that in here. If we have n minus 1 plus 1/2, that's going to be the same as h bar omega times n minus 1/2. So we're subtracting 1/2. Now this comes as a result of substituting n minus 1 into this equation. Now let's have a look at n plus 1. Well, n plus 1 is going to look like this. We're going to have n plus 1 plus 1/2. And that is going to be equal to h bar omega. Then we'll have n plus 3 on 2. So that is going 1 above n. So this is en, and this is e sub n plus 1. And here we have 3 on 2. That is just summing these two fractions. So we could keep going on and on and on, and this keeps going on forever. And we can see that only the non-negative integers are allowed. We're not allowed to have negative energies. Negative energies don't make sense. There's a contradiction. And we're also not allowed to have energies in between here. We cannot fit any energy eigenvalues in between these ones. That is why this is called a discrete energy spectrum. So the Hamiltonian has a discrete spectrum. Now that is the quantum in quantum mechanics. So the quantum in quantum mechanics is referring to the fact that these energies are quantized. They come in discrete chunks. And you can see that the difference between each of all of these guys is always h bar omega. So the difference between any two of these energies is h bar omega. So here we have to go up h bar omega, and here we have to go down h bar omega. So this is minus h bar omega, and this is plus h bar omega. And we can link that back to the ladder operators in the previous video in the quantum mechanics playlist. We found that if you apply the ladder operators to these states, these very special eigenstates, you either increase or decrease the energy by h bar omega. This is the quantum of energy. So this is the discrete chunk of energy that you can raise and lower the states with. So let's keep this in mind. These are the energy eigenvalues. These are the possible values of energy that you can measure if you perform an experiment. And these cats over here, these are the states. So we have states, and each of these eigenstates are associated with a particular eigenvalue, and that is the energy eigenvalue. And make sure you distinguish E sub n from little n. Little n is just a non-negative integer, right? It's 0, 1, 2, 3, and so on. But E sub n is the specific energy eigenvalue. We're going to be using this equation over here in subsequent videos. It's a very useful equation for the quantum harmonic oscillator. If you want to find the other videos in the quantum mechanics playlist, you can find them if you click over here.